All right, ladies and gentlemen. So what we're going to be doing today is we're going to be talking about some stoichiometry. And stoichiometry is something we've been doing so far in this unit. And so everything we've been doing from before break is all part of stoichiometry. So thinking back to everything we've been covering so far in this unit, it does give us a heads up as to what really has been happening. Stoichiometry is the relationship between the relative quantities or those relative amounts of substances in a chemical reaction or that take part in a chemical reaction. So there's a couple things that we probably want to remember when we're talking about stoichiometry. Some things that we want to remember are the molar mass, and specifically with the molar mass, we want to remember two things. The first thing being, how do we find the molar mass? Can you guys tell me how we find the molar mass? That's right. So we're going to find our molar mass when we look at the periodic table. Each element has its molar mass at the bottom of the periodic table of that element symbol if we're looking for it. The second thing is that we want to know, what does this molar mass really tell us? So do you guys remember what the molar mass really tells us? Okay, so the molar mass, yes, you guys were perfect. The molar mass tells us the amount of grams that we have for every 1 mole. And if we remember that 1 mole is just a huge number of particles that we don't really need to remember at the moment. But we do need to know that that 1 mole is the only way we can compare two different substances. If I tell you that you have 12 grams of water and you have 12 grams of iron, they're going to look a lot different. If I tell you you have 12 moles of iron and 12 moles of water, that's telling you have the same number of particles of each of those things. Even though they weigh different amounts, you have the same number of particles of each of those things. The other thing we do need to remember is that mole ratio. And specifically with the mole ratio, where do we find the mole ratio? So can anybody tell me where we find the mole ratio? Perfect. You guys are dead on right here. We find the mole ratio in our balanced equation. Once we find our mole ratio, we also need to know what we use this mole ratio to do. Can anybody tell me what it's going to be used for? Man, you guys are crushing it. So we use that mole ratio when we're trying to determine how to compare between two different elements or compounds in a balanced equation. So the only time we can set up a mole ratio is when we have a balanced equation, and the mole ratio tells us how to compare between two different elements or compounds in that balanced equation. Most of the time we are going to go from elements of the reactants to elements of the products, or elements or products back to the reactant side. So we're going to take a look at that first question on your worksheet. That first question has a lot of information there. So what we need to do is we need to look at the whole question real quick. And if we look at that whole question, it says how many moles of NaOH, sodium hydroxide, will be created when 3.6 grams of water react with excess Na. So what that's telling us is we have a reaction happening where we have sodium and we have water, and they're going to react. I'm telling you, you have enough sodium for this reaction to happen, but we have this specific amount of water, and we want to figure out how many moles of sodium hydroxide we're going to make. So what we need to do is we need to set up our arrow. We're going to go from grams of water to moles of sodium hydroxide. Is there a molar mass or a mole ratio that tells us to go from grams of water to moles of sodium hydroxide? No, there is not, because it's two different compounds. So you guys are right, there's two different compounds, so we can't do this. So instead what we need to do is we need to first convert to moles of something else. And we're going to convert to moles of water because we know we can get from grams of water to moles of water. And to do this, we're going to use the molar mass. Okay, so we're going to use the molar mass when we go from grams of water to moles of water, because that's the only way to convert between grams and moles of the same substance. Can we go from moles of water to moles of sodium hydroxide? Perfect. Yes, we can. And that's because we can use the mole ratio. So if we can do this reaction, we can have all this happen. What we're going to do is we're really going to set up our balanced equation. So to set up our balanced equation, we have our Na plus our water, and that's going to make our NaOH and our hydrogen gas. When we do this, we're going to set up our T-table, and then we're going to figure out how many sodiums, hydrogens, and oxygens we have on each side. Now, if I'm taking a look at my sodiums, how many sodiums do I have? I have 1. How many hydrogens do you have on your reactant side? That's right, you got 2. How many oxygens do you have on your reactant side? Perfect, you guys are experts at balancing equations. We got this. How many are on the product side for sodium? Awesome, 1. How many hydrogens do you have on your product side? Perfect. You guys are awesome. Even though I tried to trick you, you have 1 from the sodium hydroxide and 2 from your hydrogen to make a total of 3 hydrogens. Remember that I do like to separate them just so I can remember that there's a difference. You don't have to separate them. It is up to you whether you want to do that or not. So make your choice at some point, either now or in the future. Doesn't matter to me. But this is how I'm going to set it up every time. My last one, oxygen. How many do you have? Perfect. You guys are crushing it. You got 1. Awesome. So we have to balance that. So are my sodiums balanced? Yes, they're balanced. Perfect. Are my hydrogens balanced? No, they are not. Which side has less, the reactants or the products? Awesome. The reactants have less. So what we're going to do is we're going to multiply that by 2 to have 4. So now I have more reactants. If I multiply that by 2, I take that 2 right there, and where do I put it? Awesome, you guys are crushing it. We put it in front of our water molecule. If I put it in front of my water molecule, what happens to my water? How many do I have now? I have 2 sets of water, so I have 2 times as many H's and 2 times as many O's. So that 2 goes to both my H's and my O's, which means I have to put that times 2 to have 2 sets of oxygen as well. Now, if we look, our sodiums, they're still there. We haven't touched them, but now we're looking at our hydrogens. So now let's look at those hydrogens. We have 4 hydrogens on our reactant side and only 3 on our product side. So those don't match up yet. So what we need to do is we need to make them match by multiplying which side? That's right, we're going to multiply our product side this time. We're going to multiply that by 2. But if I put a 2 in front, am I going to put a 2 in front of everything? No, you guys are crushing it. We put a 2 only in front of the sodium hydroxide because we only want that 1 to turn into a 2. So we want that first 1 to turn into a 2, which means we're going to take that 2 and put it in front of sodium hydroxide. And now that we've done that, our sodium hydroxide, we have 2 sets of those. So we have 2 times as many NAs. We have 2 times as many oxygens. And now instead of having 3 hydrogens, how many do we have? We have 4. That's perfect. You guys are crushing this. Now that we have our 4 hydrogens, we can check, are hydrogens matched? Yes, we have the same number on each side. What about our oxygens? Do we have the same number of those on each side? Perfect. You guys are amazing. What about our sodiums? No, they are not matching anymore. So what do we need to do? We need to change our reactant side. That's perfect. So we're going to change our reactant side and we're going to multiply it by how much? Yes, we are going to multiply it by 2. And if we multiply by 2, where do I put this 2? Perfect. You guys are amazing. We're going to put that 2 in front of the sodium. And we put that 2 in front of the sodium. Now my sodiums do match and my equation's balanced. Now that I have a balanced equation, I am going to remember that if I want to put nothing in front of my hydrogen, my H2, that's fine. If you want to put a 1 in front, that also works. Either way, you have that balanced equation of 2 sodiums plus 2 waters makes 2 sodium hydroxides and 1 hydrogen. Now we're going to continue and we're going to keep going and we're going to talk about part B. So it says how many moles of hydrogen water are used if 3.6 grams of water have been used. So we've broken up that problem. We're not going to do all of it at once today. What we're going to do instead is we're going to do parts at a time. So if we look at that question, we're only doing part B, which means that we're only going to figure out how many moles of water are used if 3.6 grams of water were used. In order to do that, what we're going to do is we are going to use our 3.6 grams of water, and we're going to try and figure out how to get to moles of water. Is there a way to do that? Yes, you guys are awesome. We're going to use the molar mass. And to use the molar mass, we are going to create our molar mass by looking where? Perfect. We're going to look at our periodic table. So we look at our periodic table, we're going to find H and O. If we find the molar mass of hydrogen, it's going to be 1.01. We find the molar mass of oxygen, it's going to be 16. But that's right, we have two sets of hydrogen for water. It's H2O, so we have to multiply our hydrogens by 2 to get a 2.02. I always like to make sure all mine match up in column-wise, so I just set 16 equal to 16 because we only have one oxygen. And now we're going to add those together to get our total of 18.02 grams per mole of H2O. If we do this, what we're going to do next is we are going to remember that 18.02 grams per mole of H2O is really 18.02 grams of water that's equal to 1 mole of water. So now that we have our conversion factor, we have our molar mass, so we know that 18.02 grams of water is equal to 1 mole of water, and that comes from our molar mass from the periodic table. What we're going to do is we're going to set up our railroad tracks. When we set up our railroad tracks, we put our given in the top left corner, and our given is going to be that 3.6 grams of H2O. We want to make sure our units of grams of H2O go to the bottom, which means we're going to use the 18.02 grams of H2O here. Once we do that, we are going to realize that our units of grams of H2O can cancel, and we're only going to be left with our 1 mole of H2O, which needs to go on the top. Now we set it equal to itself, and we multiply 3.6 times 1, and we divide it by our 18.02, and we get our 0.02, and let's look at those units. Perfect, the units are the moles of H2O, so we're going to put those in as our units here. And now we can continue to part C. Now for part C, when we're looking at part C, it says how many moles of NaOH are created when the moles of H2O from problem B are used. So we're using those moles from part B to figure out our next step. So we're going to set up our idea of moles of water are being converted to moles of sodium hydroxide. How do we convert from moles of one substance to moles of another? Perfect. You guys are crushing it. We use our mole ratio. If we're using our mole ratio, we need to come up with that mole ratio. Where do we get that from? That's right. We get it from the balanced equation. So we get it from the balanced equation. What we're going to do next, we're going to find the coefficients in front of those elements or compounds that we're using. So we're finding the coefficients in front of H2O and in front of NaOH. When we do that, we know that 2 moles of H2O are needed for this reaction to happen. And we know that if we react it with enough sodium, we will make 2 moles of sodium hydroxide. We've just come up with our second conversion factor, which means that now we can set up our railroad tracks. When we set up our railroad tracks, remember our given is going to be the answer from part B. So the 0.20 moles of H2O. And remember that we want those units of moles of H2O to cancel. That means the moles of H2O from our mole ratio need to go to the bottom of our railroad tracks. See how those units are both there now? So now our units can cancel. The moles of H2O have gone away. And now we need to just put our 2 moles of NaOH up at the top. We can multiply them together. So we multiply the top together, 0.2 times 2, divide it by the 2 on the bottom, and we get our 2 moles of NaOH because our units of NaOH need to be the ones we get at the end. Have a wonderful rest of your day, ladies and gentlemen.